most people carry the same mental image of space. It is black, it is silent, and it is cold. Bitterly, absolutely, uniformly cold. The kind of cold that would swallow you whole the moment you stepped outside the safety of a spacecraft. The kind of cold that exists at the very bottom of what is physically possible, where matter stops moving and the universe goes quiet. Every science fiction film reinforces this image. The hull is breached, the air rushes out, and within moments the exposed human is either frozen solid or tumbling through the void toward an icy death. It is an image so consistent and so pervasive that most people accept it without question. That picture is wrong, not a little wrong, fundamentally, deeply wrong in ways that are far more interesting than the simple version. Space is not uniformly cold. It is not even mostly cold, in any meaningful sense. In some places it is hotter than anything achievable in a conventional furnace. The outer atmosphere of the Sun, the corona, is a plasma of 1 to 3 million degrees Celsius, and it gets hotter as you move farther from the solar surface, in apparent defiance of everything intuition says about how heat should behave. The thin, nearly invisible gas threaded between galaxy clusters is heated to tens of millions of degrees as it falls through gravitational wells, forming vast cosmic structures of searing plasma that simply have nowhere to radiate all that energy quickly enough. The region of space just outside Earth's orbit has a temperature that, averaged across a full year and accounting for both sunlit and shadowed periods, would feel not unlike a cool autumn morning on the ground. But space also contains cold that goes beyond anything achieved in the best laboratories on Earth. There are places in the universe where temperatures have dropped below the lowest temperature ever sustained in a human laboratory for more than a fraction of a second. Places where the usual rules of thermal physics break down and matter enters states that simply do not exist anywhere else in nature. Places where the distinction between a solid, a liquid, and a gas loses meaning. Places that are colder somehow than the background warmth of the universe itself, colder than the faint ancient glow left over from the Big Bang that pervades all of space in every direction simultaneously. And underneath all of this, woven into the very fabric of the cosmos, detectable in every direction you could possibly point a telescope, measurable from the deepest intergalactic void to the edge of the observable universe, there is that glow. That whisper of warmth left over from the moment, 380,000 years after the Big Bang, when the universe first became transparent to light. That glow has a temperature so specific, so precisely uniform across the entire visible sky that it functions as a kind of cosmic baseline, a floor. The temperature the universe itself has been cooling toward for the last 13.8 billion years, and which it will continue cooling toward for trillions and quadrillions of years to come. Understanding the cold of space means understanding that temperature works differently out there. It means confronting what temperature actually is at a fundamental level, not the number on a thermometer, but the physical quantity that number is measuring, and why the intuitions built from a lifetime spent at the bottom of a dense atmosphere fail almost immediately once you leave it. It means meeting the coldest natural object ever discovered anywhere in the universe. An object so cold it does not just approach the background temperature of space, but actually falls below it, absorbing the ambient warmth of the cosmos around it, rather than radiating heat of its own. It means walking through a temperature landscape that spans more than 30 orders of magnitude between its hottest and coldest extremes. And it means looking far enough into the future to see where all of this cooling is ultimately headed, and what the laws of thermodynamics have to say about the final state of everything. The word temperature gets used every day without much thought, but the concept it points to is stranger than it appears. Temperature is not a substance. It is not a thing that flows from place to place the way water does. It is not something you can hold in your hand or see under a microscope. It is a description of motion, specifically the average kinetic energy of the particles in a given system. When something is hot, its atoms and molecules are moving fast, vibrating, colliding, careening around in rapid chaotic motion. When something is cold, that motion has slowed. The particles are less agitated, less energetic, moving with less speed and force. The metal of a hot stovetop feels hot because its rapidly vibrating iron atoms are transferring their energy to the molecules of your skin at a high rate. Ice feels cold because its molecules are moving slowly enough to draw energy away from your warmer skin rather than contributing any. In both cases, what you are actually feeling is the rate of energy transfer, which is a consequence of how fast the particles in the two materials are moving relative to each other. This connection between temperature and motion is why cold has a hard limit in a way that heat does not. If temperature is average kinetic energy, then there is a point where kinetic energy reaches its minimum possible value, where motion is as subdued as physics allows. That point is called absolute zero. On the Kelvin scale, the temperature scale used in scientific contexts involving very high or very low temperatures, absolute zero sits at zero by definition. On the Celsius scale, it corresponds to minus 273.15 degrees. On Fahrenheit, it is minus 459.67 degrees. There is no temperature below that number. It is not just the coldest temperature ever measured or the coldest temperature achievable with current technology. It is the coldest temperature that can, even in principle, exist. You cannot have negative kinetic energy. You cannot have less than no motion. Absolute zero is a hard wall, not a practical limit. What makes this even stranger is that absolute zero is not quite what it sounds like. You might imagine it as the point where atoms stop moving entirely, a kind of frozen stillness where nothing happens and everything just sits. But quantum mechanics, the physics that governs the behavior of very small things, forbids that. The Heisenberg uncertainty principle is one of the bedrock results of quantum mechanics, and it states that you cannot simultaneously know both the exact position of a particle and its exact momentum to arbitrary precision. Knowing one more precisely forces uncertainty in the other. This means that if an atom were perfectly still, if its velocity were exactly zero, and therefore its position were allowed to be perfectly defined, you would have measured its momentum with infinite precision, which the uncertainty principle forbids. So even at absolute zero, particles retain what is called zero-point energy, a residual, irreducible minimum of motion that quantum mechanics will not allow to be removed. The universe, at its coldest possible state, still contains a restless quantum vibration that can never be fully extinguished. This is not a technicality. Zero-point energy has measurable consequences. It is why liquid helium, unlike every other known substance, does not solidify at atmospheric pressure, even at temperatures approaching absolute zero. The zero-point motion of helium atoms, driven by their very low mass and the weak forces between them, keeps the atoms moving too much to lock into a solid lattice. Only by applying substantial external pressure, which constrains the atoms to a smaller volume and forces them closer together, can helium be made to solidify. Every other element solidifies well before reaching temperatures this low, long before zero-point energy becomes a determining factor. scientists have gotten extraordinarily close to absolute zero in laboratories, and in doing so, they have entered territory where matter behaves in ways that have no parallel anywhere in nature. Researchers at MIT have cooled samples of gas to 450 picokelvin, that is 450 trillionths of a degree above absolute zero. The University of Bremen has achieved temperatures of 38 picokelvin during a few seconds of freefall in a drop tower, using the brief absence of gravity to remove confining magnetic fields and allow the gas to expand into an ultra-cold state. At these temperatures, individual atoms lose their separate identities and fall into a single shared quantum state, a Bose-Einstein condensate, predicted by Satyendranath Bose and Albert Einstein in the 1920s but not experimentally achieved until 1995, when teams at the University of Colorado and MIT cooled rubidium atoms to temperatures of a few hundred nanokelvin and were awarded the Nobel Prize in Physics in 2001 for the feat. In a Bose-Einstein condensate, atoms behave as a single coherent quantum entity rather than a collection of separate particles. They can be made to flow as a superfluid, a fluid with exactly zero viscosity, which means it climbs the walls of its container without any force driving it, seeps through microscopic cracks that would stop any normal liquid, and flows forever, once set in motion without slowing. This is not science fiction. It is a laboratory reality produced by cooling matter far enough that quantum physics takes over completely from classical physics. Another phenomenon that emerges near absolute zero is superconductivity, the complete disappearance of electrical resistance in certain materials, which allows electrical currents to flow indefinitely without any power input and enables the powerful magnets at the heart of MRI scanners and particle accelerators. None of this, not the Bose-Einstein condensates, not the superfluids, not the extreme quantum phenomena of picokelvin physics, occurs in space. Space is cold, but not that cold. Understanding why requires thinking about how heat actually moves, or fails to move, in an environment that has almost nothing in it. Heat moves in three ways, and two of them require matter to work. Conduction is direct transfer through physical contact. Touch a hot pan and the fast-moving molecules of the metal bump against the slower-moving molecules of your skin and transfer some of their energy. This requires physical contact between objects and works best through dense materials, where molecules are packed closely enough to interact constantly. Metals are good conductors because their electrons move freely through the lattice, carrying energy from hot regions to cold regions rapidly. Wood is a poor conductor because its molecules are not arranged to pass energy along efficiently. In everyday experience, conduction is the mechanism you feel most directly. It is why metal feels colder to the touch than wood at the same temperature, because metal conducts heat away from your hand faster. Convection is the movement of heat through a fluid, air or water, carrying warmth from one place to another as the fluid itself circulates. Warm air is less dense than cold air, so it rises. Cool air sinks to replace it. This creates circulation currents that distribute heat through the atmosphere and through bodies of water. Earth's climate is largely driven by convection. Equatorial regions absorb more solar energy than the poles. The warm air rises and flows poleward. Cooler air flows back toward the equator, and this circulation distributes heat around the planet. Boiling water on a stove involves convection. Warm water near the heat source rises to the surface, cools slightly, and sinks again. Convection is everywhere in everyday thermal life on Earth, and is one of the primary reasons that the surface of the planet does not experience the savage temperature extremes that would otherwise occur. In space, both of these mechanisms fail almost entirely. The vacuum between objects contains so few particles that conduction is effectively impossible. There is nothing to conduct heat through. The nearest approach to a medium in interplanetary space, the solar wind, is so thin that it carries negligible thermal energy to any surface it touches. And convection requires a fluid, which the vacuum does not provide. The absence of a medium means that the only way heat can travel through the void between objects is radiation, the emission of electromagnetic energy. Everything with a temperature above absolute zero emits electromagnetic radiation, which includes infrared light, visible light, radio waves, ultraviolet, X-rays, depending on the temperature. And this radiation travels outward through space at the speed of light, carrying energy away from the object in all directions. A hotter object emits more intense radiation across shorter wavelengths. A cooler object emits dimmer radiation at longer wavelengths. This is why a piece of metal glows red when heated to a few hundred degrees, but glows white when heated to thousands of degrees. The peak emission wavelength shifts toward the visible spectrum and then toward the blue end as temperature rises. This is also why the thermal environment of space is so paradoxical. The temperature of a region of space is not simply determined by how far you are from a star. It is set by the balance between radiation being absorbed and radiation being emitted. An object in full sunlight near Earth's orbit warms up rapidly, not because the surrounding vacuum is warm, but because it is absorbing a flood of solar photons, high-energy radiation from a star with a surface temperature of 5,500 degrees Celsius, delivered at the rate of about 1,360 watts per square meter at Earth's distance. Turn that object away from the sun, or put it in shadow, and it begins radiating its own heat into the cold vacuum around it. Since there is no atmosphere to slow that cooling process, and since the vacuum provides no incoming warmth of any significance, the object cools relatively quickly toward the floor set by the cosmic microwave background. The result is savage temperature swings, depending entirely on orientation. The sunlit side of the moon reaches temperatures around 127 degrees Celsius. The night side, where the sun has set, cools to around minus 173 degrees Celsius, a swing of 300 degrees across the same rocky surface, with nothing but an absence of atmosphere to make the difference. The International Space Station orbits Earth roughly 16 times per day, moving in and out of the planet's shadow with each orbit. The exterior of the station swings between roughly 121 degrees Celsius in direct sunlight and minus 157 degrees Celsius in shadow. Managing this requires a sophisticated active thermal control system. The station circulates ammonia through external heat exchangers, collecting waste heat generated by electronics, life support systems, and crew metabolism inside the pressurized modules, and radiating it into space from large panels positioned where the orbital geometry favors effective cooling. The ammonia transfers that heat to a secondary coolant loop inside the habitable sections. Without active management, the electronics generating heat on the inside and the cold vacuum pressing in from the outside would drive the station toward thermal extremes that neither the electronics nor the crew could survive. Spacewalking astronauts face a smaller scale version of the same problem. Their suits must simultaneously manage the metabolic heat from physical exertion and the radiative cooling from shadow, with no convection available to help. The suit's liquid cooling and ventilation garment, essentially a network of thin tubes carrying water next to the skin, moves heat away from the body and into a sublimator on the exterior of the suit, where water is slowly evaporated into the vacuum to carry the heat away. Spacecraft sent to the outer solar system face the opposite thermal challenge. Far from the Sun, where solar radiation is too weak to provide meaningful heating, a spacecraft must generate its own heat to keep electronics, fuel lines, and instruments within operating temperature ranges. Both Voyager probes, now traveling through interstellar space at distances of more than 150 times the Earth-Sun distance, generate heat from the natural radioactive decay of plutonium-238 in their radioisotope thermoelectric generators. As the plutonium has decayed over 4 decades, the power and heat output has dropped steadily, forcing mission engineers to progressively shut down instruments to concentrate the remaining warmth where it is most needed. The deeper thermal lesson of the Voyagers is that in the outer solar system, keeping things warm is every bit as critical a challenge as keeping things cool is near the Sun. This is why the question of what happens to a human body exposed to the vacuum of space is far more nuanced than most films portray. The famous Hollywood version, instant freezing, the body crystallizing and shattering, is wrong. In the absence of conduction and convection, a human body loses heat only through radiation. Human skin radiates heat primarily in the infrared, and this is a slow process, especially for an object at biological temperatures. A person exposed to vacuum would not freeze quickly. They would, however, die from other causes very rapidly. Without the pressure of an atmosphere outside the body, the dissolved gases in tissues begin forming bubbles, a process called ebulism, similar to what deep-sea divers experience if they ascend too rapidly from depth. The pressure of the surrounding atmosphere normally prevents dissolved gases from coming out of solution. Remove that pressure abruptly, and the gases begin nucleating as bubbles throughout the tissues. Simultaneously, the lungs, if not immediately exhaled into, experience the full pressure differential between the atmospheric air they contain and the near-perfect vacuum outside, which can rupture lung tissue. Blood does not boil in the popular sense. The circulatory system maintains its own internal pressure that prevents vaporization within blood vessels. But moisture in the mouth and on the surface of the eyes begins to vaporize almost immediately. Consciousness would be lost within about 15 seconds as deoxygenated blood reaches the brain. A person returned to pressure within 90 seconds has a realistic chance of survival with no permanent damage. This actually happened at NASA's Johnson Space Center in 1965, when a technician's spacesuit developed a leak during a vacuum chamber test. His suit pressure dropped from 3.8 pounds per square inch to 0.1 pounds per square inch in less than 10 seconds. He remained conscious for about 14 seconds, long enough to feel the moisture on his tongue beginning to vaporize, and then lost consciousness. He was rescued when the chamber was repressurized about 30 seconds later and recovered fully with no lasting effects. Cold was not the issue. Cold in vacuum is slow. It is everything else that kills quickly. To appreciate where the cold of space sits, it helps to walk through the temperature landscape of the cosmos from hot to cold, because the range is so extreme that it requires physical effort to hold it in the mind all at once. The difference between the hottest natural environments and the coldest is so vast that no single human comparison can span it. At the hot end, the core of the Sun runs at roughly 15 million degrees Celsius, sustained by the nuclear fusion of hydrogen into helium. That number describes the average kinetic energy of protons colliding with enough speed to overcome the electromagnetic repulsion between their positive charges and stick together, releasing energy in the process through Einstein's famous equivalence between mass and energy. Moving outward from the core, through the radiative zone and the convection zone, the temperature drops steadily. By the time you reach the photosphere, the visible surface of the sun, the layer from which sunlight as we see it originates, the temperature has fallen to about 5,500 degrees Celsius. That is still incandescently hot, hotter than any conventional industrial process, hotter than any flame achievable through chemistry. But it is a dramatic cooling from the core. Then something strange happens. Moving further from the sun, higher into the solar atmosphere, farther from the heat source, the temperature rises again. The chromosphere, immediately above the photosphere, has temperatures ranging up to about 25,000 Kelvin. And above that, in the corona, the tenuous, outermost layer of the solar atmosphere visible during solar eclipses as a pearly white halo, temperatures spike upward between 1 and 3 million degrees Celsius. In some active regions, during major solar flares, coronal temperatures can exceed 10 million degrees. The corona is hundreds of times hotter than the visible surface of the sun directly beneath it, and it extends for millions of kilometers into space. This is one of the most famous unsolved problems in astrophysics, and it has a name: the coronal heating problem. Heat is supposed to flow from hot regions to cold regions, not from a cooler surface to a hotter outer layer. That is a basic requirement of thermodynamics. Something is transporting energy up from below and depositing it in the corona in a form that exceeds what the photosphere could deliver through ordinary thermal conduction. Two main explanations have competed for decades. The first involves nanoflares, tiny, constant, avalanche-like releases of energy produced when magnetic field lines threading the corona become tangled and then suddenly snap and reconnect, converting magnetic energy into thermal energy in the surrounding plasma. The second involves magnetohydrodynamic waves, ripples propagating through the magnetic field from below the photosphere and depositing their energy as heat in the corona. In 2020, observations using NASA's Interface Region imaging spectrograph detected direct signatures of both magnetic reconnection and the plasma jets it produces, called nanojets, occurring during heating events in the corona. This provided the first direct observational evidence linking magnetic reconnection to coronal heating. Most researchers now believe both mechanisms operate simultaneously, but the precise balance and the question of whether they fully account for coronal temperatures remains a genuinely open problem that Parker Solar Probe, flying through the corona itself, is actively investigating. From the corona, the solar wind carries hot plasma outward through the solar system, thinning with distance as it expands into larger and larger volumes of space. Near Earth's orbit, this plasma has a temperature of around 100,000 degrees, very hot by any everyday standard. But it is also extremely thin. The density of the solar wind near Earth is about 5 to 40 particles per cubic centimeter, compared to about 25 billion molecules per cubic centimeter at sea level on Earth. This is the crucial difference between temperature and heat that becomes so important in space contexts. Temperature measures how fast particles are moving. Heat measures the total thermal energy present, which depends on both speed and the number of particles doing the moving. The solar wind near Earth has a very high temperature, but carries almost no heat to any object it encounters, because there are not enough particles to transfer significant energy. A spacecraft flying through 100,000 degree solar wind is not burned because the rate at which those fast-moving particles actually strike the spacecraft's surface is far too low to cause meaningful heating. Moving outward beyond the planets, past the orbit of Neptune and into the Kuiper belt, solar radiation has weakened dramatically, and the temperature of objects in the outer solar system is set mostly by the balance between the diminished sunlight they receive and the heat they radiate away. Pluto, at 40 to 49 times Earth's distance from the Sun, has a surface temperature of roughly minus 230 degrees Celsius, just 43 degrees above absolute zero. When NASA's New Horizons spacecraft flew past Pluto in July 2015, it found a world that had been in this deep freeze for billions of years. Its nitrogen ice plains smooth and fresh-looking despite their age, its water ice mountains rising kilometers above the surface in a landscape preserved by cold, with almost no geological activity to disturb it. In the interstellar medium, the gas and dust between star systems within our galaxy, temperatures vary enormously by region. Dense molecular clouds, the birthplaces of stars, have temperatures between about 10 and 30 Kelvin. These are some of the coldest large structures in the universe. Between the denser clouds, in the diffuse intercloud medium, temperatures average around 8,000 Kelvin, while pockets of gas heated by supernova shockwaves reach temperatures above 1,000,000 degrees. The interstellar medium is not a single thing. It exists in multiple distinct phases: cold and dense, warm and neutral, warm and ionized, and scorching hot and very thin, all coexisting within the same galaxy. Their boundaries maintained by a balance of heating and cooling processes operating across enormous distances. Between galaxies in the enormous cosmic voids, the intergalactic medium is filled with extraordinarily thin plasma. As gas falls into the filaments and clusters of the cosmic web from the surrounding voids, it is heated by gravitational compression to temperatures of 100,000 to 10 million Kelvin, a phase known as the warm-hot intergalactic medium. Despite those temperatures, this material contains almost no heat energy in practical terms, because it occupies such vast volumes at such extreme dilution. Computer simulations suggest this warm-hot phase may contain a substantial fraction of all the ordinary matter in the universe, but it is so thin and so difficult to detect that it remained observationally elusive for decades. Below all the local variation, below the warm plasma around stars and the cold molecular clouds, below the heated filaments of the cosmic web and the vast gulfs of intergalactic space, there is a floor, a baseline temperature from which there is no further escape, at least not in the current state of the universe. That floor is set by the cosmic microwave background radiation, and it measures exactly 2.725 Kelvin. The cosmic microwave background, or CMB, is one of the most important objects in all of science. It is not a star or a galaxy or a nebula. It is not located in any particular place. It is a glow that permeates the entire observable universe in every direction simultaneously. A relic of a moment that occurred about 380,000 years after the Big Bang. In those early moments, the universe was an opaque, hot plasma, a dense mixture of protons, electrons, and photons, all in constant interaction, with photons scattering off electrons so frequently that light could not travel any significant distance before being deflected. The universe was like an impenetrable fog filled with its own brilliant light. As the universe expanded and cooled, it eventually reached a temperature where electrons could combine with protons to form neutral hydrogen atoms without being immediately torn apart again by the surrounding radiation. This transition happened at a temperature of about 3000 Kelvin, roughly 380,000 years after the Big Bang. Cosmologists call this epoch recombination, and what it did was clear the fog. Without free electrons to scatter photons constantly, light was suddenly able to travel freely. The universe became transparent. The photons that were released at that moment, freed from the scattering fog for the first time, have been traveling through space ever since. They are still traveling in every direction, filling the entire observable universe. They are the CMB. The universe has expanded enormously since those photons were released, and that expansion has stretched their wavelengths. They started as visible and near-infrared light associated with a 3000 Kelvin blackbody. But 13.8 billion years of cosmic expansion has redshifted them all the way down to microwave wavelengths, corresponding to a temperature of just 2.725 Kelvin. The photons themselves have not lost their energy in the usual sense of the word. The wavelength stretching is a consequence of space itself expanding. The same photons now occupy a universe that is roughly 1,000 times larger in each dimension than the universe they were born in, which is why their wavelength is roughly 1,000 times longer and their effective temperature roughly 1,000 times lower. The uniformity of the CMB is astonishing and deeply meaningful. Measured in any direction, across the entire sky, the temperature varies by only about 1 part in 100,000. This near-perfect uniformity tells us that the early universe, at the moment of recombination, was extraordinarily smooth. Nearly the same temperature and density everywhere you looked. The tiny variations that do exist, those 1 part in 100,000 fluctuations, are not noise or measurement error. They are the preserved fingerprint of quantum fluctuations in the very early universe, magnified to cosmic scales by a period of exponential expansion called inflation, that is thought to have occurred in the first tiny fraction of a second after the Big Bang. Regions that were slightly denser attracted more matter over the following hundreds of millions of years, and eventually became the galaxy clusters and superclusters we see today. Regions that were slightly less dense became the great cosmic voids, the entire large-scale structure of the observable universe. The web of filaments and voids that stretches across billions of light years is the grown-up version of those tiny primordial temperature fluctuations preserved in the CMB. The CMB was predicted before it was discovered, which is one of the more remarkable chapters in the history of cosmology. In 1948, physicists Ralph Alpher and Robert Herman, working through the mathematics of Big Bang nucleosynthesis, calculated that the universe should be filled with relic radiation and estimated its temperature at around 5 Kelvin. Their prediction was largely forgotten. In 1964, 2 radio engineers at Bell Laboratories in Holmdel, New Jersey, Arno Penzias and Robert Wilson, were using a large horn-shaped microwave antenna, originally built to support satellite communication experiments, to conduct radio astronomy measurements. They kept finding an unexplained microwave noise signal in their data. It came from every direction equally, regardless of where they pointed the antenna. It was the same strength day and night, summer and winter. They went through every possible source of contamination they could think of. They rechecked their instruments. They cleaned a buildup of what Penzias diplomatically called a white dielectric substance deposited inside the antenna by pigeons that had been nesting there. Nothing made the signal go away because the signal was not an error. It was the CMB, the relic glow of the Big Bang, faithfully predicted by theory and now detected by 2 engineers who initially had no idea what they had found. A colleague eventually connected them with a group at Princeton University that was independently preparing to search for this exact signal. The Princeton group had been beaten to the discovery accidentally. Penzias and Wilson received the Nobel Prize in Physics in 1978. For any object in interstellar space, the CMB sets the minimum achievable temperature through natural processes. An object placed far from any star, with no other radiation source, will radiate its own heat away until it reaches thermal equilibrium with the surrounding photon field. That equilibrium is 2.725 Kelvin, because CMB photons are constantly striking the object from every direction and depositing energy. A colder object would absorb more CMB energy than it emits. A warmer object emits more than it absorbs. The equilibrium point is the CMB temperature. You cannot cool something below 2.725 Kelvin simply by removing it from all heat sources and waiting, because the CMB itself provides a constant, universal, inescapable thermal input. Absolute zero in a universe pervaded by the CMB cannot be reached by any natural process. The quantum flaw of zero-point energy and the thermodynamic flaw of the CMB both prevent it. In the constellation Centaurus, about 5,000 light-years from Earth, there is an object that appears to violate what should be an inviolable rule. The Boomerang Nebula is a dying star system in the early stages of becoming a planetary nebula, the kind of glowing shell that a star like our Sun will eventually shed as it exhausts its nuclear fuel and begins expelling its outer layers. It was first observed in 1979 by astronomers Keith Taylor and Mike Scarrett using the Anglo-Australian telescope, who named it for the bent, elongated shape it presented through their instrument. When the Hubble Space Telescope imaged it in 2003, it appeared more like a bow tie, two lobes of gas extending outward from a central star. But neither image captured the full story, and what the Boomerang Nebula is most famous for has nothing to do with its appearance. The Boomerang Nebula is colder than the cosmic microwave background. Not just cold, colder than the floor of the universe. At 1 Kelvin, 1 degree above absolute zero, it is colder than any other natural object ever measured anywhere in the cosmos. It is colder than the background warmth that pervades all of space. And this should not be possible. The CMB is everywhere. Every cubic meter of the universe contains roughly 400 CMB photons. Every natural object in space is constantly being struck by those photons and receiving thermal energy from them. For an object to sit below the CMB temperature, it must be losing heat faster than it gains it from that universal background. And since the background is inescapable, the only way to achieve this is through some mechanism of cooling so powerful and so sustained that it outpaces even the CMB input. That mechanism is rapid adiabatic expansion. The central star of the Boomerang system is a red giant shedding mass at an extraordinary rate, roughly 1,000th of a solar mass per year for the past 1,500 years. This mass ejection rate is 10 to 100 times higher than in comparable dying stars. The material is being expelled as a high-speed molecular wind traveling outward at approximately 164 kilometers per second. As this gas expands outward from the star into the surrounding space, it does work against the gravitational pull of the star and against the pressure of the surrounding material, and in doing so, it loses thermal energy. The faster and more violently the expansion, the more dramatic the cooling. This is the same physics that makes the nozzle of an aerosol can feel cold when you spray it. The gas inside the can is at relatively high pressure, and as it expands through the nozzle, it drops in temperature. In the Boomerang Nebula, this process is happening on a scale that spans tens of thousands of astronomical units, each of which is the Earth-Sun distance, and has been running for over a millennium. The cooling is so efficient that the outflowing gas reaches temperatures of around 1 Kelvin, well below the 2.725 Kelvin floor set by the CMB. Astronomers Raghvendra Sahai and Lars Åke Nyman confirmed this in 1995 using the Swedish ESO submillimeter telescope in Chile. Their method was indirect but definitive. They measured that the cold carbon monoxide gas in the nebula was absorbing CMB photons. For a gas to absorb photons from the CMB rather than being heated by them, it must be colder than the CMB temperature itself. The absorption signature confirmed that the nebula's gas had fallen below 2.725 Kelvin. Subsequent measurements placed the temperature at approximately 1 Kelvin, possibly somewhat less. Later observations with ALMA, the Atacama Large Millimeter/Submillimeter Array, a collection of 66 radio antennas in the Atacama Desert of northern Chile, revealed more of the nebula's internal structure and helped explain the unusually high mass ejection rate. The leading hypothesis, supported by the geometry of the outflow, is that a smaller companion star spiraled inward into the envelope of the red giant, transferring orbital energy that dramatically accelerated the ejection of material. This kind of binary interaction, one star absorbed by another, produces an outflow roughly 10 times faster than a single dying star can generate on its own, which is what drives the gas to such extreme cold before it disperses into the surrounding interstellar medium. The Boomerang Nebula will not remain the coldest place in the universe indefinitely. As the central stellar remnant continues to heat, shrinking, compressing, eventually igniting as a white dwarf, the ultraviolet radiation it emits will ionize the surrounding gas and warm it. ALMA observations have already detected regions near the outer edges of the nebula that are warming as the central star's output increases. Sahai and his collaborators noted that there are likely other objects in the same brief evolutionary phase scattered throughout the galaxy, momentary cosmic freezes lasting only a few thousand years before the stellar evolution moves on and the temperature climbs back toward the CMB floor. No laboratory on Earth has sustained temperatures as low as 1 Kelvin across a macroscopic volume. The coldest sustained laboratory temperatures achieved in dilute gas experiments, around a few hundred nanokelvin, are far colder than the Boomerang Nebula in absolute terms, but require microscopic samples of a few thousand atoms held in place by precisely tuned laser beams and magnetic traps, maintained for fractions of a second. The Boomerang Nebula achieves 1 Kelvin across a volume roughly 21,000 astronomical units in radius, sustained for centuries, powered entirely by the physics of stellar death. In the local interstellar cloud through which our solar system is currently passing, a region of warm neutral gas, a few light years across, embedded in the larger local bubble, itself a cavity carved in the interstellar medium by ancient supernova explosions. The gas temperature is measured at around 7,500 to 11,000 Kelvin, based on observations of interstellar neutral helium by the Interstellar Boundary Explorer satellite. This is warm in one sense, but the gas is so thin, less than 1 atom per cubic centimeter, that it has essentially no thermal effect on any solid object moving through it. Voyager 1, now traveling through this region, is cooling by radiating its own heat away, unaffected by the technically warm plasma surrounding it. It is worth pausing on that last point, because it represents one of the central conceptual confusions that surrounds the temperature of space. the local interstellar medium near the Sun is, in technical terms, hot. Its particles are moving fast, and a thermometer that measured particle speeds would return a high reading. But that same thermometer, if it were a physical object placed in that region, would cool toward 2.725 Kelvin regardless, because the density of the surrounding gas is so low that its particles would strike the thermometer surface almost never, transferring negligible energy. The object's actual temperature would be set by its radiation balance with the CMB, not by the kinetic temperature of the surrounding plasma. Temperature in a vacuum is not what it seems from everyday experience, and this distinction between the temperature of a gas and the temperature of an object placed in that gas underlies almost every surprising fact about the thermal environment of space. Comets offer a particularly vivid illustration of the temperature landscape of the solar system. A comet forming in the Kuiper belt, or the Oort cloud, spends most of its existence at temperatures of 20 to 50 Kelvin, its ices and organic molecules frozen and inert, drifting through the outer solar system on timescales of millions of years. When a gravitational perturbation sends a comet inward toward the Sun, its temperature begins climbing as the distance decreases and the solar radiation flux increases. By the time it reaches Jupiter's orbit, around 5 astronomical units from the Sun, its surface temperature has climbed to around 120 Kelvin, and some of the more volatile ices begin sublimating, releasing gas that forms the coma, the fuzzy envelope around the nucleus. By the time it reaches Earth's orbit, at 1 astronomical unit, the surface temperature can reach 300 Kelvin, and the sublimation is vigorous enough to produce the tail we associate with comets in the night sky. The comet carries its deep frozen cargo from minus 250 degrees Celsius all the way to near room temperature, delivering whatever was preserved in the cold to the inner solar system and occasionally to the surfaces of the inner planets. It helps to anchor the abstract numbers in a walk through specific temperatures across the solar system and beyond, because reading them sequentially gives a sense of the scale that a table of numbers alone cannot convey. Let's first go back TP the Sun's core, which operates at roughly 15 million degrees Celsius. The photosphere, the visible surface, is about 5,500 degrees Celsius. The corona above it ranges between 1 and 3 million degrees. Moving outward, the solar wind near Earth carries plasma at temperatures around 100,000 degrees, but at such low density that it delivers almost no heat to objects moving through it. Earth itself, at the surface, exists in the narrow band between roughly minus 89 degrees Celsius and plus 58 degrees Celsius, the extremes of recorded surface temperature. This range, which contains all of human civilization and almost all known life, represents an extraordinarily small slice of the temperature landscape of the cosmos. It is maintained by the combination of solar energy input, the greenhouse effect of the atmosphere, the thermal capacity of the oceans, and the convective circulation of air. Remove the atmosphere and these temperatures swing wildly. The Moon, at nearly the same distance from the Sun and with no atmosphere, oscillates between 127 degrees Celsius and minus 173 degrees Celsius in direct relation to whether it is in sunlight or in shadow. Mercury presents the most extreme surface temperature swings in the inner solar system, roughly plus 430 degrees Celsius on the sunlit side, minus 180 degrees Celsius on the night side. A range of over 600 degrees, produced purely by the combination of proximity to the Sun and the absence of any atmosphere to smooth out the fluctuations. Venus, by contrast, despite being slightly farther from the Sun than Mercury on average, has a surface temperature of around 465 degrees Celsius on both the day and night sides, the hottest planetary surface in the solar system, maintained by a runaway greenhouse effect that traps solar energy beneath a dense carbon dioxide atmosphere. The lesson Venus teaches about temperature in space is that the atmosphere matters as much as, and sometimes more than, distance from a heat source. Moving outward, Mars averages around -60 degrees Celsius at the surface, with swings from roughly +20 degrees Celsius near the equator on a summer day to -125 degrees Celsius on winter nights near the poles. Jupiter's visible cloud tops are about -110 degrees Celsius. Saturn's cloud tops are similar. Uranus, despite being much farther from the Sun, presents an interesting anomaly. It appears to radiate almost exactly as much heat as it receives from the Sun, unlike the other outer planets, which all radiate significantly more heat than they receive, indicating retained internal heat from formation. Uranus seems to have lost its internal heat, possibly as a result of a large impact early in its history that tilted the planet and somehow disrupted the convective transport of heat from the interior. Its cloud top temperatures reach -195 degrees Celsius, making it one of the coldest planetary surfaces in the solar system. Neptune, farther from the Sun, is actually somewhat warmer at its cloud tops, around -200 degrees Celsius, because it still retains significant internal heat. Pluto averages around -230 degrees Celsius at the surface. When New Horizons flew past in 2015, its instruments measured the surface temperatures of different regions in detail. Nitrogen ice plains at around -233 degrees, water ice mountains at slightly warmer temperatures, and a thin nitrogen atmosphere, with a surface pressure about 100,000 times less than Earth's at sea level. The world had been in this deep, preserving cold for billions of years, and it showed in the geology, ancient features preserved in pristine condition, a heart-shaped nitrogen ice plain that showed evidence of glacial flow far too slow to have been observed in any human lifetime. Beyond Pluto, in the scattered disk and the Kuiper belt, objects receive so little sunlight that their temperatures are determined primarily by the balance between very weak solar heating and radiation to the CMB. Most Kuiper belt objects have temperatures somewhere between 20 and 50 Kelvin, barely warmer than the coldest molecular clouds in the galaxy. These objects are effectively time capsules. Their surfaces preserve chemical compositions from the early solar system largely unchanged, because the cold prevents the chemical reactions that would alter them at higher temperatures. At the temperatures that prevail in the coldest regions of space and in the most extreme laboratory experiments, matter does not behave the way everyday experience would suggest. The transitions that occur as temperature falls toward absolute zero reveal properties of matter that have no counterpart at higher temperatures, and in doing so, they reveal something fundamental about the quantum mechanical nature of reality. The first dramatic change happens at relatively accessible temperatures. Nitrogen, which makes up about 78% of Earth's atmosphere, liquefies at -196 degrees Celsius, or 77 Kelvin. Oxygen liquefies at -183 degrees Celsius. Hydrogen, the lightest element and the most abundant in the universe, liquefies at -253 degrees Celsius, just 20 Kelvin above absolute zero. These are temperatures found in the outer solar system. Pluto sits at roughly 43 Kelvin, cold enough that any hydrogen present would be a liquid or a solid. Most of the outer solar system's ices are water, nitrogen, methane, and carbon monoxide, frozen at temperatures where they would be gases on Earth. Below about 4.2 Kelvin, liquid helium undergoes its first phase transition. It becomes superfluid. The helium atoms, now moving so slowly that their quantum mechanical wave functions begin to overlap significantly, undergo a transition related to Bose-Einstein condensation. They cease to behave as individual particles interacting through collisions and friction, and start behaving collectively as a single quantum fluid with exactly zero viscosity. The consequences are spectacular. Superfluid helium flows up and over the walls of its container, in a thin film driven by the van der Waals attraction between the helium and the container wall. The molecular stickiness that normally produces only a small capillary effect is now completely unopposed by viscosity, and the helium creeps upward and over the rim and down the outside. It passes through microscopic pores that would stop any normal fluid. If set in circular motion in a bucket, it continues spinning indefinitely without slowing down, because there is no viscosity to extract energy from the flow. Below about 2.17 Kelvin, the lambda point, helium-4, enters a deeper superfluid phase where even more exotic phenomena emerge, including the ability to carry heat as a wave rather than by diffusion. This second sound, a quantum mechanical wave of temperature, allows heat to propagate through the fluid at a definite speed, like a sound wave, rather than spreading diffusively the way heat moves through ordinary materials. This has been exploited in cooling systems for scientific instruments that require extremely stable, low temperatures. The Large Hadron Collider at CERN uses superfluid helium to cool its superconducting magnets to 1.9 Kelvin, colder than the Boomerang Nebula, and these magnets produce the intense magnetic fields needed to guide beams of protons around the 27-kilometer ring at nearly the speed of light. Superconductivity, the other great phenomenon of low temperatures, emerges in many metals and alloys when they are cooled below a critical temperature that varies by material. In conventional superconductors, the mechanism involves electrons pairing up, counterintuitive as this sounds, since electrons repel each other, through interactions mediated by vibrations in the crystal lattice. These Cooper pairs obey different quantum statistics from individual electrons and can move through the lattice without any scattering. Below the critical temperature, every electron pair moves coherently, and the resistance drops to exactly zero. Not nearly zero, exactly zero. A current established in a superconducting ring in 1954 was still circulating with no measurable decay decades later. The technology is real and pervasive. Every MRI scanner, every particle accelerator with superconducting magnets, every radio telescope using superconducting receiver circuits relies on this phenomenon produced by cooling matter toward the quantum cold. None of this occurs naturally in the cosmos except through human technology. The CMB temperature of 2.725 Kelvin is cold enough that helium in space would be a superfluid, but helium is not found in macroscopic liquid pools in space under natural conditions. It exists as a trace component of gas clouds, too dilute to pool. The Boomerang Nebula's 1 Kelvin is genuinely below the lambda point of helium, but the helium there is a gas, not a liquid. The exotic quantum phenomena of low temperatures are a feature of the laboratory rather than the cosmos. They are what happens when humans deliberately strip thermal energy from matter, exploring what the universe would look like if the cooling it is slowly undergoing on cosmic timescales were achieved instantaneously. The cosmic microwave background is not just a curious fact about how cold space is. It is among the most information-dense observations in all of science, a single measurement that encodes the entire history of the universe from its first 380,000 years to the present day, and which has provided some of the most precise answers to some of the deepest questions about the nature and history of everything. The tiny fluctuations in the CMB, those 1 part in 100,000 temperature variations across the sky, are not random noise or instrumental artifacts. They are the direct imprint of physical processes operating in the first moments of the universe. Before recombination, the early universe was a hot plasma of protons, electrons, and photons in tight thermal contact. Any slightly overdense region of plasma attracted more matter gravitationally, compressing inward, but as it compressed, it also heated, building up pressure that pushed back against the compression. The result was acoustic oscillations, sound waves in the most literal physical sense, propagating through the hot plasma of the early universe. These waves were established at the moment of inflation and rang through the plasma for 380,000 years, until recombination froze the pattern in place. The CMB is a snapshot of those waves at the moment they stopped. A photograph of sound in the early universe, preserved in the distribution of temperatures across the sky. The pattern of these fluctuations, their amplitude, their angular scale, the relationship between temperature variations and polarization, carries an extraordinary amount of information. The first peak in the power spectrum of CMB fluctuations corresponds to the scale of sound waves that had completed exactly one full compression rarefaction cycle before recombination. Measuring that scale tells you the total energy content of the universe, because the geometry of space, whether it is flat, curved positively like a sphere, or curved negatively like a saddle, affects how that scale projects onto the sky. The location of that peak tells us the universe is geometrically flat to within less than 1% precision. The relative heights of subsequent peaks encode the ratio of ordinary matter to dark matter, because ordinary matter couples to photons while dark matter does not. A universe with more ordinary matter relative to dark matter would show a different peak ratio than one with less. The measurements nail down the baryon density, the density of ordinary matter, to around 5% of the universe's total energy content, with dark matter contributing about 27% and dark energy making up the remaining 68%. All of this, and more, is extracted from the temperature of the CMB, from the fact that some patches of sky are at 2.7251 Kelvin, while others are at 2.7249 Kelvin. The European Space Agency's Planck satellite, which operated from 2009 to 2013 and released its final cosmological data in 2018, measured these fluctuations with enough sensitivity and angular resolution to determine the age of the universe to 13.8 billion years with an uncertainty of less than 1%, to measure the Hubble constant, which is the current expansion rate of the universe, with sub-percent precision, and to constrain models of inflation to an unprecedented degree. The temperature of space, specifically the detailed structure of the 2.725 Kelvin glow, contains within it a story that reaches back to the first moments of time. There is something profound in this. The cold of the CMB is not passive background warmth, it is an archive. Every photon in the CMB has been travelling since 380,000 years after the Big Bang, carrying information about where it started and what density environment it was released from. The universe wrote its early history in temperature, and that history has been preserved in the cold of space for 13.8 billion years, waiting to be read by creatures who developed the mathematical tools and the instruments to read it. One of the most counterintuitive things about space is that hot and cold are not simply about location. They coexist in the same regions of space simultaneously, in different things, at the same moment. A spacecraft orbiting Earth sits in solar wind plasma at 100,000 degrees, while its sun-facing surface is at 121 degrees Celsius, and its shadow-facing surface is at minus 157 degrees Celsius. A molecular cloud contains pockets of coronal gas at millions of degrees, sitting next to dense regions at 10 Kelvin. The interstellar medium is not in thermal equilibrium, and it never has been, because the heating processes that drive its temperatures are local and varied, and because the gas is too thin to exchange heat between its different phases efficiently. This coexistence of drastically different temperatures in the same general region of space is a consequence of how temperature works in a near vacuum. In the dense environment of Earth's lower atmosphere, collisions between gas molecules happen billions of times per second, and these collisions transfer energy between different parts of the gas with extraordinary efficiency. Any region that gets hotter shares its heat with adjacent regions almost immediately. This constant rapid mixing drives the atmosphere toward thermal equilibrium on relatively short timescales, and is why the temperature on Earth's surface varies only over a range of a few hundred degrees, rather than the millions of degrees found in the gas just a few hundred kilometers above. In space, the collision rate drops to essentially zero. Particles in the interplanetary medium near Earth collide with each other roughly once a day, compared to billions of times per second in air at sea level. In the interstellar medium, collision rates are orders of magnitude lower still. Without collisions to distribute energy efficiently, different populations of particles can maintain completely different temperatures indefinitely. Electrons in the solar wind are measured to be significantly hotter than the protons in the same volume of space, because the two particle types equilibrate with each other slowly, and the heating mechanisms driving the solar wind preferentially heat one over the other. This is not an anomaly or an oversight. It is a fundamental feature of plasma physics in low-density environments. The temperature versus heat distinction that appears throughout any serious discussion of space becomes most stark in the context of the warm-hot intergalactic medium. Plasma at 10 million Kelvin, strung out in filaments and halos around galaxy clusters, has individual particles moving at speeds of thousands of kilometers per second. Each particle is extremely energetic, but the plasma is so dilute, maybe one particle per 10 cubic meters in the void regions, that its total heat content per unit volume is negligible compared to, say, the air in a warm room, where the particles are moving at only a few hundred meters per second, but where there are trillions of times more of them per cubic meter. High temperature in a vacuum can mean almost no heat at all. This matters practically for thinking about space exploration. A human body or a spacecraft in interplanetary space is not heated to dangerous temperatures by the solar wind plasma, despite that plasma's six-figure temperature. What heats objects in space is radiation, the infrared and visible light from the sun, not the particle temperature of the ambient plasma. And conversely, what threatens a future spacecraft attempting to pass close to the sun is not the million-degree corona, but the intense radiation flux from the much cooler photosphere below it. The Parker Solar Probe, which passes within roughly 9 solar radii of the Sun's surface, uses a carbon foam heat shield to protect against the radiation from the photosphere. The shield surface reaches about 1,400 degrees Celsius. The spacecraft behind it operates near room temperature. The corona's million degrees barely register, The cold of space is not simply an absence. It is not just what is left over when heat goes away. Cold plays active, creative roles in the universe that are at least as important as the roles played by heat. It is the environment in which some of the most consequential processes of cosmic evolution occur, and without it, the universe would be profoundly different. Star formation happens in the cold. The giant molecular clouds that produce stars are cold, 10 to 30 Kelvin, for a reason directly related to why stars form there at all. For a cloud of gas to collapse gravitationally and eventually ignite as a star, gravity must overcome the thermal pressure, pushing the gas outward. Higher temperature means higher pressure, which means a more massive and denser cloud is required before gravity can win. Lower temperature means lower pressure, which means less massive clouds can collapse more easily. The cold of molecular clouds is not incidental to star formation. It is a prerequisite. The Sun formed in a cold molecular cloud. Every star that has ever burned in the Milky Way formed from gas that had been cooled to temperatures near the bottom of the cosmic temperature range. The universe makes stars in the cold. The chemistry that builds complex molecules also happens in cold. In warm environments, molecules are constantly being broken apart as energetic collisions overwhelm the chemical bonds holding atoms together. In the near-zero temperatures of interstellar molecular clouds, molecules forming on the surfaces of dust grains can survive long enough to build up complexity. Astronomers have now detected over 200 distinct molecules in interstellar space, including surprisingly complex ones: water, ammonia, methanol, ethanol, formaldehyde, acetaldehyde, glycolaldehyde, or simple sugar, and amino acid precursors have all been detected in dense molecular clouds. In 2009, glycine, the simplest amino acid and one of the molecular building blocks of proteins, was detected in samples returned from the comet Wild 2 by the Stardust spacecraft. Comets are themselves products of cold chemistry. Formed in the cold outer disk of the early solar system, comets are mixed assemblages of water ice, carbon dioxide ice, complex organic molecules, and silicate dust, a frozen record of the chemistry that prevailed in the primordial solar nebula before the planets formed. When a comet falls inward and heats up near the Sun, its ices sublimate and release those molecules, which can rain down on the inner planets. There is a serious scientific hypothesis, the panspermia hypothesis in its chemical form, that suggests organic molecules delivered by cometary impacts played a meaningful role in providing the chemical raw materials for the origin of life on Earth. If so, the cold of the outer solar system, preserving those molecules for billions of years unchanged, was not just a feature of the solar system, but a part of the story of life. The cold of the early universe also set the initial conditions for everything that followed. The moment of recombination, when the universe cooled to 3000 Kelvin and became transparent, froze the density fluctuations of the plasma into the pattern that eventually became the large-scale structure of the cosmos. The subsequent cooling of the universe over hundreds of millions of years eventually brought gas down to temperatures cold enough for molecular hydrogen to form, which was a prerequisite for the first stars. The population 3 stars, massive and short-lived, which lit the universe for the first time about 200 million years after the Big Bang. The first stars could not have formed without that cooling. The cold was the mechanism that allowed the universe to organize itself from a featureless plasma into a structured cosmos of stars and galaxies. In the solar system's outer darkness, the cold has preserved an archive. The surfaces of Kuiper Belt objects and comets retain chemical signatures from the early solar system in a condition that would long since have been erased by geological activity in the warmer, inner solar system. The organic molecules in carbonaceous chondrite meteorites, which are meteorites derived from the most primitive and chemically unprocessed asteroid material, contain amino acids, nucleobases, and other biologically relevant compounds that formed in the cold of the early solar nebula and survived billions of years because the cold prevented the reactions that would have altered them. Every sample returned from an asteroid, every comet we catch and analyze, is a message preserved in cold from a time before the Earth existed. The universe is colder now than it has ever been at any previous point in its history. This is not an accident or a local peculiarity. It is the fundamental direction in which the universe has been moving since the moment it began. The Big Bang was not just an explosion of matter and energy. It was the beginning of a cooling process that has continued uninterrupted for 13.8 billion years and will continue for an almost incomprehensible duration into the future. In the first second of the universe's existence, temperatures were approximately 10 billion degrees Celsius. In the first 3 minutes, conditions were hot enough for nuclear fusion to occur freely throughout all of space, not just in the cores of stars, but everywhere, fusing hydrogen into helium and leaving behind the elemental abundances we observe today. After about 3 minutes, the universe had expanded and cooled enough that free space fusion ceased. The proportions of hydrogen, helium, and trace amounts of lithium set in those first few minutes are essentially unchanged across most of the observable universe. This prediction of Big Bang nucleosynthesis is one of the most precise and well-confirmed results in all of cosmology. By 380,000 years, the universe had cooled to 3,000 Kelvin and the CMB was released. By the time the first stars ignited, perhaps 200 million years later, as gas clouds cooled enough to collapse, the average temperature of the universe was already well below the surface temperature of those stars. The formation of stars did not warm the universe in any global sense. The stars were islands of heat in an increasingly cold sea. Since the CMB was measured at 3000 Kelvin at recombination and measures 2.725 Kelvin today, the universe has cooled by a factor of about 1,100 over the last 13.8 billion years. This cooling will continue. The expansion of the universe stretches the CMB photons further with every passing billion years. 10 billion years from now, if the expansion continues at its current accelerating rate, the CMB will have cooled to roughly 1.4 Kelvin. A trillion years from now, it will be a fraction of a Kelvin. The accelerating expansion is itself the most important fact about the universe's thermal future. In the late 1990s, teams studying Type 1a supernovae, which are stellar explosions used as standard candles for measuring cosmic distances, discovered that the expansion of the universe is speeding up over time, not slowing down as gravity would dictate if matter were the only significant component. The implication was that the universe contains a form of energy, now called dark energy, that acts as a repulsive pressure operating at cosmic scales. The discovery, which earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics, means that the universe will expand forever, and will expand at an increasing rate, inexorably driving the CMB temperature lower. As the expansion continues and the CMB cools, the universe passes through a series of eras in its thermal history. We are currently in the stelliferous era, the age of stars. Stars will continue forming for roughly the next 100 trillion years, although at diminishing rates as the supply of cold gas available for star formation is gradually exhausted. After that, the last stars will cool and go dark. The universe will enter the degenerate era, consisting of white dwarfs cooling toward absolute zero, neutron stars, and black holes. Even the white dwarfs will eventually cool to the temperature of the CMB, though this takes longer than the current age of the universe by many orders of magnitude. Black holes survive everything. They are the final structures to persist in the universe after all other matter has either been consumed by them or dispersed. But even black holes are not eternal, according to theoretical physics. In 1974, Stephen Hawking showed through a calculation combining quantum mechanics and general relativity that black holes emit radiation from their event horizons as a consequence of quantum effects near the boundary. Virtual particle pairs being created near the horizon, with one falling in and one escaping. This Hawking radiation means that black holes slowly lose mass and energy, eventually evaporating completely over timescales that depend on their mass. A black hole with the mass of the Sun would take roughly 10 to the power of 67 years to evaporate, an incomprehensibly longer time than the current age of the universe. A supermassive black hole of 1 billion solar masses would take closer to 10 to the power of 100 years, a Google years. When the last supermassive black hole has evaporated through Hawking radiation, the universe will consist of nothing but the products of that evaporation: photons, gravitons, and elementary particles, dispersed across an almost inconceivably vast and expanding space. No stars, no planets, no structure of any kind. The CMB, already chilled to an effectively undetectable temperature, will continue cooling asymptotically. This state is the heat death, or big freeze, not a violent end, but a gradual, inexorable approach toward maximum entropy, where no temperature differences remain anywhere in the cosmos to drive any process or sustain any structure. The term heat death is deliberately and interestingly paradoxical. It sounds like a hot ending, but it is the coldest possible one. In thermodynamics, heat refers to the ability to do work, and heat death is the state where all heat in the thermodynamic sense has been dissipated, where energy is perfectly and evenly distributed across the universe, leaving no gradients from which work can be extracted. Every process, every reaction, every computation, every ordered structure requires a difference in energy or temperature from one place to another. Life requires a difference between the energy in food and the lower energy state of metabolic products. A clock requires a difference between the energy stored in its spring and the environment. Stars require a difference between the gravity pulling inward and the thermal pressure pushing outward. In the final state of the universe, all such differences are gone. Nothing can happen. The universe is not hot in that state. It is cold, asymptotically, eternally, irreversibly cold. The temperature of the CMB having dropped so far that the distinction from absolute zero is meaningful only to mathematics. The final temperature is almost certainly not zero. Current understanding of dark energy, modeled as a positive cosmological constant in Einstein's equations, suggests that the universe approaches a de Sitter state with a non-zero residual temperature, determined by the Hawking temperature of the cosmic event horizon. This temperature is estimated at around 10 to the minus 30 Kelvin, a number so close to absolute zero that no physical process could distinguish it from zero, but technically non-zero. The quantum flaw and the thermodynamic architecture of the universe in combination preventing the final step. There is something worth sitting with in all of this, something that goes beyond the numbers and the physics and the exotic states of matter. The cold of space is not simply the absence of warmth. It is an active feature of the universe, one that has shaped everything from the formation of the first atoms to the chemistry that seeds life, to the eventual fate of every structure that exists. It is the direction in which the universe has always been moving and will always move, written into the foundations of thermodynamics and cosmology simultaneously. The picture of space as simply, uniformly cold misses almost everything. The thermal landscape of the cosmos is one of the most varied and dynamic environments imaginable. Within a single galaxy, temperatures span more than 10 orders of magnitude between molecular cloud cores and the gas heated by supernovae. Within a single stellar system, a spacecraft can swing from above, boiling, to below freezing, simply by changing its angle relative to the star. The Sun heats its own outer atmosphere to temperatures its surface cannot reach. A dying nebula 5,000 light-years away cools its gas below the background temperature of the universe itself, briefly and extraordinarily, before the stellar remnant heats everything back up. And threading through all of it, from the surface of Mercury to the largest cosmic voids, constant in every direction and every location anyone has ever looked, the 2.725 Kelvin glow of creation persists. That glow is itself the most remarkable temperature measurement ever made. It is not merely a fact about how cold interstellar space is. It is a thermometer that reads the age of the universe. It is a photograph of the cosmos at 380,000 years old, preserved in temperature across the entire observable sky. It is a record of density fluctuations that seeded all the structures we see today. It is the evidence, direct, measurable, confirmable by any instrument pointed at any part of the sky, that the universe began in heat and has been cooling ever since, carried along by its own expansion toward an endpoint that lies trillions upon trillions of years in the future. It is also, in a deeply strange way, the reason we can exist at all. Life requires ordered structures, molecules, cells, organisms. Ordered structures require low entropy, a degree of arrangement and organization that tends to decrease over time unless energy is put in to maintain it. The Sun provides that energy by being a hot object radiating into the cold of space. The temperature difference between the Sun's surface and the cold background drives the entire energetic economy of the biosphere. Photosynthesis, the foundation of almost all life on Earth, works by absorbing high-quality solar photons and re-emitting them as a larger number of lower-energy infrared photons, using the energy difference to build ordered organic molecules. The cold of space is as essential to life on Earth as the Sun itself. Without a cold enough universe to radiate into, the Sun could not sustain the temperature difference that makes energy useful. The cold is not just a backdrop to life, it is part of the mechanism. The cold we now live beside, that 2.725 Kelvin whisper in the microwave background, is a measure of how far the process has come. And the cold that is still coming, the long, slow cooling of the remaining 100 trillion years of the stelliferous era, the longer cooling of the degenerate era, the near eternity of the black hole era, and the final asymptotic approach toward a temperature that mathematics can express, but physics can never reach, is a measure of how much further it has yet to go. All of known history, every star ever lit, every civilization, every discovery, every moment of awareness or wonder or beauty, occurring in the narrow, improbable, astonishingly rich band of temperature between the impossible heat of the beginning and the approaching cold of the end. If what you have just heard makes you want to go further into the physics of how the universe began, what dark energy actually is, where the largest and coldest structures in the cosmos are found, or what the final state of everything looks like in more detail, this channel covers all of it. New scripts go up on a regular schedule. Hit subscribe so you don't miss what's next.